Hello everyone. In this video, I will continue with page 21 in our Boolean booklet. I will prove the DeMorgan theorem using truth table, and I will prove absorption theorems using both algebra and truth table. As you recall, in previous lesson, we are talking about postulate theorems. We proved them as well. And we also proved the distributive rule using algebra and also using the truth table. So let's continue, and we are going to prove this DeMorgan theorem using the truth table. Okay, so we are proving this DeMorgan theorem right here. So proving the DeMorgan theorem, I will analyze what I need to include in my truth table. So I should have A, B, C. Then I found that I have not A, not B, not C. Then I should have a column of A or B or C. Then I should invert the signal. I should also have not A and not B and not C. So in this case, the total column I should have should be 9. Alright, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so let's fill in our truth table. A, B, C, not A, not B, not C. And I should have A or B or C. I should have this signal inverted, and I should have not A and not B and not C. And in the end, I should prove that these two are actually equal to each other. Alright, so let's fill in our 0 and 1. Again, we will repeat that we always have the first 4 as 0, the last as 1. Okay. Alright, okay. So we input the signal of A, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 0, 1, 0, 1, 0, 1, 0. So A or B or C, in this case, I will have the first one as 0, but the rest of them will be 1. Then I invert the signal. Alright, okay. So the last one, I should have this 3, but will be an AND gate. Okay, so don't forget this one is an OR gate, A, B, C. This one I pull that into a NOR gate. This one I should have invert the signal, and then I pull them into an AND gate. Okay, so A, B, C, A invert, B invert, and C invert in this case. Okay, so what do I have? I need to get 1, 1, 1, so this I should have a 1. Because of an AND gate, as soon as I see a 0, then I know that my output has to be 0. So all of them will be 0. Okay, so compare this column with this column. I can see that they are equal, and you can conclude that you have proven this two Boolean expressions, they are equal to each other. Alright, so let's move on to our absorption theorems. Okay, I will prove the first 3 absorption theorems using algebra. Okay, so using algebra, what I will do, I repeat this, and as soon as you see the bracket and factors, you should multiply everything inside the bracket. So A dot A plus A dot B. A dot A is equal to A and plus A dot B again. And you can factor out the A's now, so it's 1 plus B. So 1 plus B is equal to 1. So you have A dot 1. So in the end, you have it equal to A. So there it is. They are proven equal to each other. Alright, okay. So go to the next one. Again, I will rewrite my left-hand side. And I know that I should multiply this inside the bracket. I should have A dot A inverted plus A dot B. Okay, so now I would like to take a look at A dot A inverted and what kind of theorem that I should use in this case. Okay, so if you go back to our page 21, you see that you are using this theorem right here. A dot A inverted should be equal to 0. Okay, so right here I should have this equal to 0 plus AB. Okay, so at this point I would like everyone to analyze that you are having an OR gate. Okay, and you have a signal of 0. You OR that with a signal of AB. So the only time you have a 0 is when both of these are equal to 0. So in this case, the signal AB will take over. So therefore, in this case, you should have equal to AB. And I can see that and that equal to each other. So I have proven it. Okay. Alright. Let's move on to the next one. I have A plus AB. I would like to remind everyone that as soon as you see the same, you factor it out. So A will be 1 plus B. Okay, what is 1 plus B? 1 plus B, in this case, is equal to 1. Again, it's an OR gate. As soon as you see a 1, your signal has to be 1. So I can write it as A dot 1. What is A dot 1? It's equal to A. So again, it's proven. Okay, so that equal to that equal and proven. So I would like to prove the absorption theorems using truth table. Okay, and from this absorption theorem, we will also prove this absorption theorem right here. Okay, so again, I will have just 2 inputs, right? 2 inputs. So I should have 4 combination of 0 and 1. Alright, okay. So in this case, I should have A, I should have B, I should have the column for not A, I should have the column for not AB, I should have the column for A or B, and I also should have a column of A or not AB. So 6 altogether. So A, B, not A, not AB, I should have A plus B, and the last column I should have A or not A and B. Okay, so again 0, 0, 1, 1, 0, 1, 0, 1 should be 1, 1, 0, 0 here. The next one should be the 2 columns. So this one I should have a 0, 1, 0, 0. Next one I should have A, B. So this one I should have 0, 1, 1, 1. And the last column should be A in this column. Okay, so there and there. So give me a 0. As soon as I see a 1, it's a 1. As soon as I see a 1, it's a 1. As soon as I see a 1, it's a 1. Okay, so in the end, you see this and that are exactly equal to each other. Alright. So please note that if I have the absorption theorem written in this form, I can also have the absorption theorems written in this form as well. So to see that they are equal to each other, in this question, I should have A, I should have B, I should have A inverted, I should have A, B, I should have A inverted or with AB, and I should have A inverted or B. Alright, 6 columns altogether. Okay, so A, B, A inverted, AB, A inverted, AB, and I should have A inverted plus B. Okay, excuse me. So we have 0, 0, 1, 1, 0, 1, 0, 1, 1, 1, 0, 0. This one I should have all 0 except for the last row. Okay, so A inverted. As soon as the 1, I should have a 1. So this should be a 0 and a 1. And I should have A inverted with the B. Okay, so OR gate. So as soon as I see a 1, it's a 1. So I just have 0 there. Alright, so this is the 1. In the end, you see that they are the exact match of 0 and 1. So therefore, this one they are equal and proven. Alright, thank you.